force here. So 2. We want to talk about how work depends on displacement and force. And we want to talk about 2 ways to and then there's 2 ways to do the same work. So what I really want to do here is that I want to give you sort of a conceptual way of looking at things, and you go from there. Hey, you guys hear the dogs. You probably hear the doorbell. Hey, this is the facts of working from home. I wish it could be better, but that's what happens, man. So
I completely understand, Carlos.
so so what I want to do here is that I want to come in and I want to just give you a very simplistic picture, and then I want to get way more technical. So the first thing that we want to do here is that I want to give you just a very, very, very simple picture. So here's a simple picture on work. So one of the things that we imagine here is that we have a block. And what we're going to do with these blocks is that we're going to do a couple of things here. You could imagine that I apply the same force on both blocks. Okay, and so what we really want to do here is that we want to push this block. One way that we can do this is that we could move this block this far. So if I move this block this far, then clearly when I look at the displacement of this block, it's that amount. But what happens if I actually move the block twice as far? Right? So if I move this block twice as far, I clearly have a much larger distance, and so therefore I have to do more work. I mean, that's not rocket science. If I tell you to carry a box, half a block, and then I tell you to carry a box, the whole block, clearly moving the whole block costs you more work. So in this case here, we can clearly see that if I talk about the force being the same in both situations and the displacement being like this, well, of course, this has less work than that. Not a surprise. What I really want to focus on is that this conceptual issue here. If I have a block that's twice as big, and now I move it initially this distance right here. What I'm seeing here is that this force, because it's twice, let's say twice as massive, dude, that thing has to be twice as big. Of course it has to be twice as big. You're moving twice as much. But now you're only going once the distance. So when you look at this work here, if I really do double the distance and double the force, what you're seeing here is that I could have a situation where if I double the force and I do once the work and once the distance, then that these 2 works must be the same. In other words, there's 2 ways to do the same amount of work. Okay, so what I want to do here is I want to set up a situation. But now I want to mathematically calculate it. So the situation that I want to set up here is that what we want to do here is that we want to imagine that. So here's my example now. And this example that we want to do here is that we want to say that suppose 1 is moving a refrigerator onto a U-Haul truck, right? A U-Haul truck. So the picture that I want you to imagine is that I want you to imagine this picture here. So I'm going to give you both scenarios right here. So typically, when we're thinking about a U-Haul truck, right, we kind of imagine that there's this bed that you're going to take this thing onto, right? So you got this truck bed that you're going to get it onto here. And when you're doing this here, of course, the thing that you're thinking about is that your ass better have a ramp, right? So if you got a ramp and you put the refrigerator onto this ramp here, what you're seeing here is that you can move that refrigerator up to the ramp because you know how to push on a ramp as you're going up here, right? So we know that this guy has some angle, and of course, this is a ramp situation, and the whole goal here is to take that refrigerator and do what? Put it right here. You want to take that guy and you want to put it onto the bed of the truck, right? That's the case here. Now, what I'm going to do here is that I'm going to be real silly, and I'm going to just say, let's say you're some dumbass that decides, you know what, they charge more to use a ramp, so therefore I'm not going to use the ramp. One, if you do that, you're obviously an idiot, but I know you guys wouldn't do that. And so in this scenario here, what are we talking about? Well, we have the same situation, right? But now what we're doing here is that you got the refrigerator down here. And when you're looking at that refrigerator again, your whole goal is to do what? Is to raise that refrigerator all the way up here. And you got to admit, there's got to be something wrong with you if you go like, oh yeah, I think it's a real good idea to come right here. And now I'm going to take my hands here and I am going to lift this thing. All I know is that you're going to be crying a river of tears here because you decided to save money and go with the no ramp situation. So the question is this, it seems really silly here. Who does the greater amount of work? And as you can probably surmise, they both do the same amount of work. That is crazy. Already there's a problem with the word work, right? If you're saying that this guy picking up the refrigerator straight up and lifting it is doing the same work as this guy, then guess what? You already have a problem with language. But that is the fact. And so what I want to do here is that I want to mathematically calculate it so you could see what I'm talking about. Here we go. Case 1. What are we going to do? We push it up the ramp, right? That's what we want to do. We want to push it up the ramp. So here we go. So what we want to do this time is that we want to start off with the free body diagram and then calculate the work. Okay, so here we go. So what we're going to do here is that let's set up an incline. So I imagine that I have an incline. And the way I set up this incline here is that you could imagine that if I have my refrigerator right here, what am I going to do here? Well, what I'm going to do here is that I know that there's a series of forces here. So, of course, there's the force of mg and the normal force, and of course, the force that's being done, that's the pushing force. Now, to make things simpler, we're going to assume that there is zero acceleration. So what I'm saying here, that we have an assumption of acceleration equal to zero. In other words, v is equal to a constant. I don't have to do that, but it just makes it nicer. So there's my free body diagram. And then I'm going to make another crazy assumption, right? And the assumption is that there is no friction. And you're probably going like, wait a minute, if there's no friction, how do I get this thing to even go up there? Well, we could say that it's being slid. And the guy who's pushing it up the ramp has, I don't know, has very, very, very special shoes. You know, I can get around that thing. We could say that there's a guy down below off the ramp pushing it up by their hand. So there's lots of ways to do that. So that's our free body diagram. So what we need here is that we need the details of the ramp. So what I'm saying here is that when I look at the details of the ramp, I have a distance. So when I look at the distance here, in other words, I'm going to say that the length of the ramp is a distance d from here to there. And then the height of the ramp is h. And because this angle is here, I can rewrite h in terms of d so that this is d sine of theta, since h is the opposite, not the adjacent. So here we go. So what I'm going to do here is that sets up the picture. And what you're going to see here is that in this case here, we are doing work. But let's be real specific here. How are we doing work? We are doing work in the direction of the displacement. So this is the force along the direction of displacement. Because I'm moving the full displacement, if I want to say that. And then I have to multiply this by the displacement. So that's what I mean by this picture here. And in this situation, this is what I'm calling case number 1. And then there's a second case, which is the other case with no ramp that we want to look at. So the question is, what is the minimum force required to push this thing up? So the minimum force must be what? Well, the force of the push must counteract the force along the x direction here. Okay? So that means here that the net work done when you're going up the ramp, and that's what I mean by ramp, is that it's case number one, that must be the pushing force times the displacement. But wait a minute, that must be mgx, and that mgx times the displacement, but we know how to write down mgx. So if I use the angle here, I can write mgx as what? mg sine of theta, or I can write this as mg cosine of theta, where it's got to be 90 minus theta. I'm going to use this one just because it's cleaner. So then this guy's going to read mg sine of theta times d. So what you're seeing here is that, check this out. When I write this down, this guy is what? A smaller force. And this guy right here is a longer distance. Check this out. Look at the picture. This is our second picture. Smaller force, bigger distance is going to give me a work. It's the same type of thing. Okay, so now let's go. So now I know what that work is. So in other words, in summary, I'm going to say here that the network, the network going up ramp is then going to be mg sine of theta times d. Now let's go to case 2. So when I go to case 2, remember what case 2 is. The case 2 is with no ramp. So here, okay, there's no ramp, right? If there's no ramp, what's really happening here? If there's no ramp, you are then taking the refrigerator, right? And you're going to lift this sucker up. How high? You're going to start here and you're going to lift it how high? You're going to lift it this high. It's got to be the height of what? It's got to be the height of the incline. So when you're looking at this thing here, here's my incline. So if I look at my incline, there it is. So you're moving it up this far. And how high are you moving it up? Well, we know that this is D. We know this is theta. And we know that that guy is H right there. So what you're doing here is that in this case, you're actually taking the full force, the full weight of this thing, and you're literally lifting this up here. So this is the force where you're just, it's the lift force to do that. And of course, what you're finding here is that you are feeling the full weight of the refrigerator. So now this is different here. And the way this is different here is that now I'm going to be looking at the work doing what? The work in this case is now different. This is the full force. And now what you're doing here is that this is the displacement along the direction of the force. It's a different way of doing work. You can do work 2 different ways. So then check this out. So when I look at the work, this is now going to look at the network with no ramp. And if I do that, we already know that this is the work of lift times the displacement, but the displacement this time is just h. So then check this out. So this guy has to be what? mgh. But wait a minute. Didn't we just say what h was? H was d sine of theta over here. So if I come in here, what I'm really seeing is I got mg times what? D sine of theta. And so what you're seeing here is look at the position of the sine theta. Up the ramp, it was with the weight. Now, with no ramp, the sine is with D. And so this guy is the net weight with no ramp. But check it out. Look at the difference. Here, what are you seeing here? Here, you're seeing a larger force. Whereas here, you're seeing a smaller displacement. And so what you're finding here, as an incredible as it seems, right? This is unbelievable, right? It's unbelievable. I could see I spelled unbelievable wrong, but I'm moving right on. That the work with a ramp is equal to the work with no ramp, right? I mean, this is just plain and simple, man, strange and counterintuitive. The problem is, it's true. It's absolutely true. And so what you're really seeing here is that, yes, you can do the same net work. It's just that in one case, you're just shifting the sign from one place to the other. That is insane. And the thing about it here is that you do this all the time. You may do this all the time. And as a everyday application here, it's about, using a car jack to lift a car, to change a tire. You do this all the time. If you ever change a tire. And so what ends up happening with the car jack is that you have what? You have a hydraulic jack, and it operates on fluids. So you'd have to really get together and understand the ideas of a fluid to really do that. But in Physics 11, I actually we set up a system that could actually show this here. And what happens here is in a jack, what you typically have, let's say this is the jack right here. And what you find here is that you typically have a little notch here. Let's say that there's this little notch that you can come in here and you can take this is what they used, in the old days, they used to call this a tire iron. Nowadays, they cause rotations here. And what really happens in this scenario here is that when you're looking at this tire iron, what you're doing here is that this is essentially equivalent to doing the following thing here. It's almost like this is acting like a fulcrum. Okay, here's my little fulcrum right here. And what you're doing here is that you're taking like a teeter-totter bar that looks like this here. So you have this teeter-totter bar, and what happens here is that as you change this thing and you move it, what you're seeing here is that you're actually doing this type of thing. And what you're looking at here is that here you're moving it a larger distance. Here you're moving it a smaller distance. And so what happens here is that the hydraulic jack, what it does here is it does not change the force. Okay? It does not change the force. So excuse me, I said force, work. The work transferred through the hydraulic jack is identical to the work that you do. So that means if you do a small force here, the hydraulic jack then does a big force there. So the only reason you can lift your car is this, that the work of the person is then equal to a small force over a larger distance. Then when you look at the work of the jack, it turns out that they're identical. So what happens? What does the jack do? It applies a bigger force over a smaller distance. That's why you have to keep jacking up the car a whole bunch of times, because you're moving a very small distance. But that's exactly what this statement is. Even though it seems counterintuitive, it's physically possible and it happens.